Welcome everyone to section 5. This is the chain rule. In this video, we're going to do a little bit of a review. The claim is that the chain rule deals with compositions of functions. We want to do a little bit of a kind of algebra review. What are these compositions of two functions? And then I'm going to give you the statement of the chain rule, and we want to be able to certainly understand that and see how we can apply it to a few problems. So, first of all, right, functions, they can do a lot of things, right? They can sum together, that you can take the difference between the two, you can product them together, you can take the quotient, right, or divide the two. But there's another thing that functions like to do that numbers really don't do, and that's eat each other, right? So you can take one function and put it inside of another function, and this is what was called, right, a composition. So kind of going in kind of the classical direction, maybe in your algebra class or something like this, if I give you a good old function f, and a function g, then you can compute the composition, which is f composed with g. That is, g is inside of the f function. So basically, everywhere that you see an x, you're going to put a g of x. So f is x squared, but instead of putting an x there and squaring it, I'm going to put a g of x there. So g of x is 3x plus 1. And so this right here is the composition f of g of x. Again, just replacing everywhere I had an x with a g of x, whatever that happens to be. In this case, 3x plus 1. So this is how we can compute a composition, and this is kind of a classic problem that you've probably done in your favorite algebra class. Again, this is called the composition of f and g. This is one kind of common notation right here, the f of g of x sort of deal. It's also sometimes denoted with this open circle right here. This is another way to write f composed with g. Sometimes when students see this, they think fog, right? So maybe you thought this at one point as well. So we're doing calculus class, right? So we want to know, how do we take the derivative of compositions of functions? We know a product rule, we know a quotient rule, we know a sum rule, difference rule, right? Those things are pretty easy. But how do we take the derivative of a composition of functions? And in order to do this, really we need to be able to go backwards. That is, we need to be able to recognize composition. So a function that is really the composition of two functions, we need to be able to express it as such, right? So we want to be able to recognize these things. All right, so let's try this. Here we have a function h of x, which is sine of x squared plus x. So I want to find functions f and g so that I can write h as the composition of two functions. So again, we're kind of going in this backwards direction. We're taking this function that is really a composition of two functions and being able to express it as such, right? What is it the composition of? Okay. Well, notice with the composition, there's an outside function and then there's an inside function, right? And so the outside function kind of eats this inside function. In this case, and we'll get good with practice on these things, you can see that x squared plus x is being inputted into the sine function. So if I was to go ahead and say, well, here's an inside function, right? So g of x is maybe a good inside function. So in this case, maybe x squared plus x. Then our outside function is going to be, well, sine in this case. So I'm going to do sine of x though. So this is going to be sine of x. And of course, we can double check, right? So we propose a solution. I think this is it. But then using our skills, right, our algebra skills, we can go ahead and double check this. So let's do f of g of x. So that would be f, so sine, but instead of x, right, everywhere I see an x here, I'm going to do a g of x. So g of x is x squared plus x. And you can see that indeed you do get back to where you started. So we found the functions f and g so that we could write this more complicated function as a composition. All right, now that we can kind of go in this backwards direction, that is kind of identify compositions and what they're made up of, we want to be able to take the derivative. And so here it is, again, 2.5 is called the chain rule. This deals with compositions. So if g is differentiable at x and f is differentiable at g of x, then the composition, which, so I'm denoting with this a capital F here, and this is going to be the compositions of f and g, which is again defined by, another way you can write this is f of g of x, that is that g is being inputted into the f function, is also differentiable at x, and the derivative is given by f prime of x is equal to, and we'll take the derivative of the outside function, leaving the inside alone for right now. Then we multiply by the derivative of the inside. And that right there is the chain rule. Another way to write this is in our good old Leibniz notation, and this actually looks, particularly nice if you write it in the Leibniz notation. So I'm going to go ahead and substitute, instead of g of x, I'm going to write this as u. And in which case, if you want to take the derivative of capital F with respect to x, then this is going to be the derivative of capital F with respect to u times the derivative of u with respect to x. Again, this is basically your g function. So this one right here is the g prime, and then this one right here is the derivative of this outside with respect to just u in this case, or with respect to g of x. So you don't do anything to that inside. And now again, this looks especially nice because it looks, if we think of these things as fractions, you can kind of see that, oh, this du and du would cancel and you would just get df dx. Okay, so I will show you how to actually use both of these things, right? And I mentioned right here in this remark that Leibniz notation should not literally be thought of as a fraction, but it still gives us a good way to remember the chain rule, right? It looks like the du's just cancel. All right, so I want to go back to our good old function that we did in example 5.3, and I would like to take the derivative of this using my standard notation, right? So we've already decided that the outside function was sine, and the inside function was x squared plus x. And that was from example 5.3. Now, let me go ahead and follow then this one right here. So, okay, I want to take the derivative of this. So I'm going to take the derivative of f. So this is going to be derivative of sine is going to be cosine. But now notice that this is not just f prime of x. It's f prime of g of x. So, okay, instead of just x, I'm going to plug in x squared plus x times the derivative of g of x. So the derivative of g of x is going to be 2x plus 1. So again, by recognizing what is the outside function and what is the inside function, right, we were able to take the derivative of our composition of functions, h of x. And here it is. And in this video, we're just getting introduced to the chain rule, so we're taking it a little bit slow, but eventually we're going to get very fast at these things. And we'll just be able to look at this. And right, when I look at this now, I see the derivative of the outside function, sine, goes to cosine. Leave the inside alone, so just do g of x here, times the derivative of the inside. And so by the time that maybe a quiz or an exam comes around, you'll be able to just do these style problems in one line. It'd be very nice. Okay, but then let's also go ahead and write this Leibniz notation. Maybe it was a little bit confusing. Let's go ahead and find the derivative using this good old Leibniz notation. So this is where we let u be equal to our g of x. So g of x, which in our case, right, g of x is the inside function. So this is going to be x squared plus x. So then we can write our function h as just, so this is going to be h of u now, I suppose, is going to be sine of u, right? Because now this is sine, but instead of x squared plus x, well, we're denoting that with a u. So this is going to be sine of u. Okay, so in our particular one, since we don't have a capital F, we have an h, right? It would be, we want the derivative of h with respect to x. So it's going to be the derivative of h with respect to u times the derivative of u with respect to x. And this little dot here, there we go. So I want the derivative of h with respect to u. All right, so here is h of u. Let's take its derivative with respect to u. And well, we have it in terms of u. Great. So the derivative of sine is cosine. And if you'd like to, the derivative of u, again, this is with respect to u, would be 1. So if you considered, kind of a chain rule here, this would be just times 1. So that's the derivative of h with respect to u. Now we want the derivative of u with respect to x. Well, here's our u function, right? It's x squared plus x. So if I go ahead and take this derivative, again, with respect to x, this is going to be 2x plus 1. And therefore, the derivative of h with respect to x is going to be equal to cosine of u times du dx, which in this case is 2x plus 1. Now u was something kind of that we made up for this problem, so let's go ahead and substitute back in. Everywhere we see a u, we're going to write x squared plus x. So I'm going to write cosine of x squared plus x times 2x plus 1. So this is, again, how we use this Leibniz notation. Again, we get the same result, right? Using the standard notation or using the Leibniz notation, we get the same result. But the big thing is just finding a way that works for you. And again, hopefully we're going to get to a point here after we do a few more practice problems where you become very quick at these things. But again, this is kind of why it works. All right, that's it for this video. Go ahead and take a break, and then our second video is just going to be practicing the chain rule. So we're going to be applying it to a lot of problems. I'll see you then.